just, I'm gonna show you the kinetic theory of gases, the relationship between pressure and temperature, and also the Maxwell-Boltzmann distribution of gases.
Okay, right. You're wrong. I did it 3 times.
So of course, the ideal gas law is kind of present there every time you're doing pretty much any chapter. It's kind of present, ever-present equation, which says that the product of pressure and volume is equal to number of moles of gas times the gas constant times temperature, which is NKT. So it's in our formula sheet. I think in chemistry class they cover the nRT more often. And then here we kind of use them interchangeably, nR versus nk. So n is the number of moles. N is the number of particles. And then R is the gas constant, universal gas constant. And then K is Boltzmann's constant. And then the units of this is the R is 8.315. 8.315 joule per mole Kelvin. I'm not sure if they use that as much in the chemistry class, but more often they use the other one, 0.08214 liter atmosphere over mole Kelvin. This one is more often used in chemistry. I kind of like this one better because it makes you see that R is connected to units of energy, joules. Whereas liter atmosphere, you don't really see. Liter atmosphere, it has nothing to do with energy, you think. So why is that the same as units of energy? Well, liter is units of volume, and atmosphere is units of pressure. Is pressure times volume energy? Is units of pressure times volume energy? Well, according to this is moles, right? This is R. What's the units of R? Joule per mole. So you see, if this is joule per mole Kelvin, if this is Kelvin and this is mole, Kelvin cancel, so P times V should be units of energy. Okay, the other way to look at it is to go back to Physics 101 and to say, how is work defined? Integral of force times distance, right? Newton times over meter, sorry, Newton times meter, and that's defined as a joule, right? But for gases, we don't really deal as much with their force on the gas. We deal more with the pressure on the gas. So we can change this to what? F divided by area times dxa. Right? So if I take a gas and I exert a certain pressure on it, and let's say I compress it, or I allow the gas to expand, right, by a certain volume, how much work has the gas done? So notice what? If you take the physics 1 equation and you tweak it a little bit to make it more appropriate for gases, what do you notice? F over A is pressure. A times dx is dV. So pressure times volume should give you energy. So if pressure times volume is energy, the rest of this should work out so that they give you units of energy. See? So if this is moles, Kelvin, R should have units of energy, which goes to joules right there. You see? But then you say, from here, how do you go to liters and atmospheres? Well, you kind of convert, you say 1 atmosphere is how many pascals, right? I can show you the conversion in a second. And then you can kind of convert from meter cubed to liters. So in chemistry, they often use that because they're dealing with things that are milliliters, liters, and a lot of times the pressure is given in atmospheres. Okay, what is Boltzmann constant? So this one should also have units of joules, right? So if this is particles, this one should be units of joule per particle, Kelvin. That's pretty much the only difference. So then you just have particle cancel, then you're left with K. So K is gonna be 1.38 times 10 to the minus 23 joule per Kelvin. 1.38 times 10 to the minus 23 joule per Kelvin. And then you could also put particle here. Joule per Kelvin per particle. Now, one constant that you don't see you see here explicitly is Avogadro's number. What is Avogadro's number? It's written as Na. It's how many particles of gas are in 1 mole of a gas. So 6.028 times 10 to the 23. Is it?
2.8 or 2.3?
Okay, I think it's 238, you're saying. Okay. Particles per mole of a gas. So that means in every mole of a gas, that's how many particles there are. So now I can use the Avogadro's constant to connect n with little n. This tells you how many total particles are in the gas. This tells you how many moles are in the gas. If I multiply number of moles by Avogadro's number, then I get the number of particles. You see? So number of particles is equal to number of moles times Avogadro's constant. Because Avogadro's constant is saying per every mole of a gas, this is how many particles there are. So if I multiply this by number of moles, mole cancel, what do I get? Total number of particles. So big N is equal to little n times Na. You see? So now if I substitute that here, what are you going to get? Big N is equal to N, Na, K, T. You see that? So you could substitute into this equation either the big N, little n times Na. Then what should happen? If I relate this to this, what should happen?
R equals
R equals to what?
NAK.
NAK. So the gas constant is literally Boltzmann's constant, right? R is equal to NAK. Have you guys ever heard of that before? No? Cool, huh? So it's kind of like this is what we're calling things, just giving them names, but they're all kind of related. So gas constant R, what's Avogadro's constant? 6.0238 times 10 to the 23. Boltzmann's constant is what? 1.38 times 10 to the minus 23. What should happen? Boom, boom, right? So Avogadro's number is 10 to the 23. Gas constant, Boltzmann's constant 1.38. This cancels. 1.38 times 6.02 should be what? 8.315. Is that? So basically this number times Avogadro's number is this. You know? Huh? Does it give you?
8.3128.
It's not quite, huh? Let me see here.
Yeah, but the Avogadro's number.
Let's get this down to the more accuracy.
Mm.
Avogadro's number 6.022 times 10 to the 23. Okay, so this one was wrong. 6.022 times 10 to the 23. Right? Avogadro's number. Okay, now let's look up Boltzmann's constant.
It still makes it small though. Which one?
Okay, 1.381. You can do 1.381 times 10 to the minus 23. So if you remember two of these, you can always derive the third one. If you remember Avogadro's number and Boltzmann's constant, you can derive the gas constant. Okay, now comes the universal, is it called universal gas constant? Yeah? Look at all the different versions of it. Okay, maximize it, come on. Right, 8.314. 8.314 joule per Kelvin per mole. Okay, so it's saying 8.314. Does that come out? 6.022 times 1.381?
1346 something.
Huh?
Yeah, it come on.
8.314?
If I hold all the decimals, yes.
Yeah, probably, yeah. 8.314 joule per Kelvin per mole. But look at all the other versions. 0.0821 liter per atmosphere per Kelvin per mole. 0.0831 liter bar per Kelvin mole. 8.314 pascals. Well, that's the same. So how do we convert? Let's practice converting from here to here to the chemistry version.
Okay.
How do we do that? Eight 8.314 joule per mole Kelvin. Joule would be what? Joule is a Newton. You know what? Let's just write it as a Newton meter. Newton meter is a joule, right? And then you can say what? We need to transfer to oh, here it is. You're gonna do like this. Multiply this by meter squared, divide by meter squared. Aha. That's how you convert. Multiply by meter squared, divide by meter squared. So then what do you end up as? 8.314 Newton times meter cubed over meter squared mole Kelvin. Newton per meter squared is a Pascal. It's unit of pressure. 8.314 Pascal times meter cubed over mole Kelvin. Then you can say 1.013 times 10 to the 5th pascals is 1 atmosphere. Remember from Physics 101, atmospheric pressure at sea level. Right? And then what's the conversion between meter cubed and a liter? 1 meter cubed is 1,000 liters. So meter cube cancel, Pascal, Pascal cancel, you get like that. So basically you're dividing 8.314 by 1,000, cancels this, so you're dividing it by 101.3. This one will cancel 3 of these, and then you move the decimal over. So basically you're dividing the 8.314 version by atmospheric pressure at sea level, 101.3 kilopascals. That should give you this version, 0.08214. It's kind of like dividing it by 100, but it's a little bit more than 100, right? So if it's a little bit more than 100, it would make sense that it's the 3 changes to a 2, you see? See, that's why this one is 0.0821, whereas there's 8.31. See, so it's not perfectly 100. So that's a good kind of connection between all of these constants, the big N, the little n, the R, the K, the Na. The next thing to do is to say, where does this one come from? This equation. Pressure is 2 Nk over 3. Nk is 3/2 Nkt, 3/2 nRT. What's this all? Where does this all come from? And that one comes from the derivation of the kinetic theory of gases. So they take usually, let me see if I can find them there. Yeah, that's where it comes from. So you say, so it says equilibrium properties. Pressure and kinetic, and in kinetic model of gases, the pressure is equivalent to the force exerted by the atoms hitting and rebounding from a unit area of the gas. Consider gas of n molecules, each of mass n, enclosed in a cube of volume L cubed. So that's kind of where the derivation comes from. So you assume as if the gas is enclosed in a cubic box, but once you derive the equation, you don't have to assume that anymore. So you say, it's like this. L, 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 and then you have the box. This is kind of going back, hitting here, and then the gas particle is exerting a force on the box, and the box in return is exerting a force back on the gas molecule, right? A certain force F, like that. So then it says, consider gas of n molecules. When a gas molecule collides with the wall of the container perpendicular to the x-axis and bounces off in the opposite direction with the same speed, an elastic collision, the change in momentum is given by, so it's a simple physics 1 thing again. Remember, force is equal to the rate of change of momentum over time. F is dp dt, right? So then it says here, this guy is coming in, so we're assuming that the gas is coming in with a certain the speed, v initial, in the, right? And then it's coming back out with the same final velocity. You see? So what's the change in momentum of the gas? So you can take the initial velocity, here's the wall, break it up into x component and y component, the initial y. Then it bounces back like this, the final. We can break that into final component, the final x, the final y. So the y component of the velocity is not changing, right? V initial y, V final y is the same. So if, let's say the marker comes like this, hits it, and goes like that, the y component is down, and the final y component is down. It's not changing, but the x component, it's going like this, then coming back out, you see? So the V initial x, V final x, the momentum in the x direction is changing, okay? So we say momentum final in the x minus momentum initial in the x gives you the change in momentum, delta P. You see? So then, if it's a perfectly elastic collision, what's going to happen? This final velocity in the x is going to be same as the initial velocity in the x, but opposite direction. So V final x is going to be negative V initial x, right? So then this is going to be m V final x minus m V initial x is change in momentum, and then m V final x is going to be negative m V initial x, negative V initial x, delta P. You see, so that's what they're doing there. M P initial x minus P final x, P initial x minus P final x is negative of P initial x, so then that's 2 P initial x, which is 2m Vx. I see. So negative 2m V initial x is delta P. So just take its absolute value for now and concentrate on that. So the next part of the argument is P is the momentum, I and F indicate initial and final momentum, X indicates that only the X direction is being considered, and V is the speed of the particle. The particle impacts one specific side wall once every 2L over Vx, where L is the distance between the opposite walls. In other words, we don't really know the time of contact of the ball with the wall, right? It's a very short time. But, so in other words, it's something like this. If we were to graph the force versus time, let's say at t equals to 0, the particle is here. So the particle experiencing no force, you see? Then as soon as it hits this, it experiences a spike in the force, right? Then it goes back, right? Then it goes back to here, right? And then it experiences another spike when it gets to here. So let's say at t equals to 0, it starts here. The particle starts here. It's going like this. So let's say at t equals to 0, the particle is here, it's going down. So this is t equal to 0. So it goes down, no force is experienced. It hits the thing, it experiences a force. Then it comes back, it experiences a force here. Then it goes back. Let's assume the bottom is way down here. So then it goes back. So then it experiences another force. You get the idea? So now if I want to know the average force during one time interval, right? In other words, what's the average force experienced by from the particle from this wall? The average force is the average of all the zero and the spike. You see, kind of like what we do in my physics one, where we do the car problem, right? We say zero velocity, zero acceleration, and then you have a spike acceleration. So then you say the average force is the change in momentum divided by the total time it takes for the particle to go from the left side and hit the right wall, right? So so it says the particle impacts one specific side wall once every 2L over Vx. Oh, okay, because once the particle has hit here, it's got to go and come back to hit it again. So that's why they did 2L over Vx, right? In other words, this is the right wall, right? This is the left wall. This is the right wall again. You see, you get the idea? So if I want to know the average force experienced by the particle from the right wall, I say force average is delta P over delta T. What's delta P? 2mv initial x divided by what's delta T? The time it takes for, once it hits it, for it to go and come back. So what is that time? Twice the length of the box, L2L, divided by the x component of the velocity, right? The x component of the velocity, which tells you this way and then this way. The y component doesn't change the time. So you divide it by v initial x. And that's going to equal to the average force. So you see, average force is going to be delta P over delta T. So then the 2's canceled, right? Because the change of momentum was 2mvx, and then this is 2L, this canceled, you get what? mv initial x squared over L. Okay, so then what's the next thing they're gonna argue? Then they're going to say the total force on the wall is nmvx squared average over L, where n is the number of particles. See, so that's just on one particle. So then the average force on n particles is going to be n. Okay, then the next step is to do what? Where the bar denotes an average over the n particles. Since the motion of the particles is random and there is no bias applied in any direction, the average square speed in each direction is identical. Vx squared average is Vy squared average, Vz squared average. You see? So this is the average of the square of the velocities.
So the delta T, that's from just the right wall to the left wall?
It's from the right wall back to the right wall. Yeah, the time. So it's like you're taking, actually I should have done like this. You're going from, let's say the left wall was this one. So from left wall to left wall, you're taking this whole average time. Then from here to average time. Then you're doing it the same thing, like that. From right wall to right wall, left wall to left wall, you're taking the average value of that. Because what you're trying to do is to determine the average force experienced on an individual particle from a particular wall of the box.
Yeah. So it has to, yeah,
You have to do
For the
2.
initial.
That's why this 2 is canceled. Yeah. Okay, the next thing they're gonna do is to say Vx squared is Vy squared, which is Vz squared, so that makes sense. Okay, then comes the 3. Where did the 3 come from? Look at this. So then they're gonna say the average of the square of the velocity is the sum of the average of the square plus the y squared plus the z squared, right? So in general, the velocity of the particle is gonna be some random direction, right? So v squared. So then you're gonna say v squared is equal to vx squared plus vy squared plus vz squared. Right, a simple vector addition, right? So then you're gonna say average v initial x squared is average v y squared, which equals v initial z squared. Then you're gonna say v squared is equal to v initial squared. So this comes from symmetry, But this idea comes from just vector addition. V squared is equal to v initial x squared plus v initial y squared plus v initial z squared. So this is just simple vector addition. Vector addition in 3D. Right? Then you use the symmetry in here, right? You put the symmetry and you say, okay, v squared is equal to 3v squared average, right? I like how this derivation comes about. V initial x squared average, because all 3 of these are the same. Okay? Then what's gonna happen? I believe that they're gonna substitute here v initial x squared is equal to v squared average over 3. Then they're gonna put it into here. Let's see. So let's see, go down. Okay, nice. So now the next step is to go here and b squared over 3l. Okay, then the next thing to do would be to say what? The force is exerted on an area of L squared. Therefore, the pressure of the gas is force over the area. So then you divide this by one more L squared, right? So force divided by L squared is pressure. Then you're gonna have L cubed. Well, that's equal to the volume of the gas. Volume of the box, right? Over 3V. Oh, then you see PV popping up. Pressure times volume is N over 3 mv squared, right?
Wait, but you can't really say that, right? The velocity initial x squared is equal to the vector addition in 3D,
I can't say that.
right?
Why?
Because it's v squared is from there, so you can't say on top of that the v initial, yeah, that you can't say that is equal to the right side because it's
No, because if this is equal to this, which is equal to this, then if you sum it up, you're gonna get 3 of these. Then I can divide both sides by 3. I can say v initial x squared is 3.
okay.
In other words, I'm
Oh,
saying
that's right.
that the average force exerted from one wall on a random particle that has a certain velocity, let's say coming towards me, then it's gonna be the number of particles times the mass times the velocity that it has squared divided by 3.
I missed
Yeah.
that part down there.
See, divided by 3.
Where did the L cube come from?
Oh, because I divided pressure over L squared. So I literally divided this by L squared.
Okay.
Then the L squared L became L cubed. and which became volume. So far we've derived the equation that the pressure on the gas times the volume of the gas is equal to the number of particles times the mass of each particle times the average of the square of the velocities divided by 3. Remember, what units should pressure times volume have? Energy, right? Joules. So, okay, V squared, I can see a joule thing going on here, because that's kinetic energy, right? So I know this has to have units of mv squared. So then the next thing they're gonna do is to say, well, kinetic energy is equal to 1/2 mv squared, right? Ke. So the total kinetic energy, it says, this is the first non-trivial result of the kinetic theory because it relates pressure and macroscopic property to the translational kinetic energy of the molecules, which is a microscopic property. You see, pressure is something is known as a macroscopic property. So it's what we call a property that kind of develops when you have a bunch of particles, you know. And so we see pressure, but then what is pressure? Well, then it's telling you the pressure times the volume is 2/3 of the kinetic energy. So the kinetic energy, so here is what happens. The kinetic energy total of the gas is gonna be what? 1/2 times the mass of each particle times the square of the velocities times the number of particles. All right, so each particle is gonna have a kinetic energy of 1/2 mv squared. And then if you have n particles, the total kinetic energy is gonna be this, right? But then here, I can't just substitute this by kinetic energy because there's a 3. So then what I can do is I can say n mv squared average is equal to 2 kinetic energy. Then substitute that there, then I can say PV is equal to what? 2/3 of kinetic energy of the gases. So if somebody told me then define what the pressure of a gas is, I can literally use this as one of the definitions. I can say the pressure of a gas is 2/3 of the kinetic energy of the gases, of the particles, divided by the volume of the container they're in, right? That could be definition of pressure. Pressure is a macroscopic quantity, kinetic energy microscopic. See? Well, there's more to discuss on this, but it's a good time to take our break. So we'll come back 1:30, continue it. Whew, a lot of material.